Okay, so we just finished talking about reflection symmetry. So the next one that we're going to talk about is rotation symmetry. So these are basically the things that we want to talk about with rotation symmetry. Recognize and describe rotation symmetry, use tools to analyze designs, and then design shapes that have specified symmetries. Basically, we want to be able to recognize and describe it, and then include the center of rotation and the angle of rotation. So this is going to be kind of our main focus on this one. And then the success criteria, 1, 2, and 3 are pretty much the big ones that we're going to be looking at with this unit. So if you look at, this is actually on page 8, not on page 9. Okay, so if you have your book, your kaleidoscopes, hubcaps, and mirrors, rotational symmetry is where you can rotate the shape in a certain direction to another position where the shape looks the same as it did originally. So if you can imagine taking this pinwheel and just rotating it either in a counterclockwise or a clockwise direction, and every time you rotate it so that one of the points moves to another point, it's basically going to look the same every single time. So you just continue to rotate it around. And if you can imagine, so then this would be the center of rotation right here. So if you imagine like putting a pin right here or sticking something in there to like a pinwheel, and then just spinning it around, your outside edges are going to move and it's going to spin on this little spot right here. So if you look, we've got some pictures up here. 2 of these pictures also have reflection symmetry. So if you could imagine taking a mirror and just placing it down the mirror, or sorry, down the middle of some of these, you know, where would you be able to fold that picture so that it looks exactly the same, so that both sides look exactly the same? So the 2 pictures that also have reflection symmetry would be your snowflake and your wagon wheel. The center of rotation is the point where you rotate the figure. So your center of rotation for the wagon wheel, or for the windmill, would be right in the center there. For the snowflake, again, it's going to be right in the center, and then also for the wagon wheel, it's going to be right in the center. The angle of rotation, this is really important. Okay, the angle of rotation, it's the smallest angle that you can turn the figure in a counterclockwise direction, and it doesn't really matter whether it's counterclockwise or not. It just has to be in a certain direction, so it looks the same as it does in its original position. The angle of rotation, in order for it to be an angle of rotation, has to be less than 360 degrees. Otherwise, it doesn't have rotational symmetry. So is less than, sorry, other way. Math teacher does more stuff. Is less than 360 degrees. So the angle of rotation is measured in degrees. Okay, measured in degrees. And then these are just the vocab words that we have talked about. The one that we haven't talked about is the order of rotation. And the order of rotation is the number of times that a rotated shape matches its original image. So if we can go back to the windmill here, the number of times that we could rotate this would be 1, 2, 3, 4. And so the order of rotation for this one would be 4, because that's how many times it would take for us to start here, spin it all the way back to the beginning. If we start with this one, there's 1 rotation here, 2 rotations here, 3 rotations here, 4 rotations here, 5 rotations here, and then 6 rotations here. So the order of this rotation would be 6. And then for the wagon wheel, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rotations. So the order of rotation for this one would be 12. So in order to find the angle of rotation, this slide might help to kind of illustrate a little bit better what we're talking about when we're talking about rotational symmetry. So if you can imagine Okay, so I think we were talking about, this might help to see kind of how rotational symmetry works. So if you can see that top layer, if you rotate it once, it's still going to look exactly like it did before. I'm not exactly on the center here. This a little bit help. That might be a little better. But you can see that it matches up again. And then if you rotate it again, and you can kind of see the black dot. Okay, so you can see that it's, as you rotate it, it's coming back. And it's not exact, sorry. It's not exactly cooperating with me today. But you rotate it again, you can see it matches up, and rotate it again, you can see it matches up. So for this one, if you talk about the order of rotation, your order of rotation for this one would be, there's one rotation here, 2, 3, 4, 5, 6, 7. So the order of rotation would be this one. And we could do the same thing with the windmill. Take the windmill, and we'll try and get it a little bit closer this time. But if you take that, you can see the black dot is the starting point. So how many rotations does it take to get back to the original spot? Well, if you rotate it 1 time, 2 times, 3 times, 4 times, now we're back to where we started. So the order of this rotation would be 4. With the snowflake, this one's hard to get exact. If you rotate, so there's 1, 2, 3, 4, 5, 6. And so what you notice is that with each rotation, after one rotation, so this is considered a rotation because from here to here, it still matches up. So each one of those little designs is matching up with the next design. Okay, so there's 2, 3, 4, 5, 6. Okay, so in order for it to have rotational symmetry, you have to be able to make it look like the original picture when you rotate it around. So in order to find your angle of rotation, okay, so the first thing we need to do is we have to find what the order of rotation is. Well, if we take a triangle, you can start and rotate it from here to here, from here to here, and here to here. So a triangle, an equilateral triangle, would have an order of 3. Well, if you need to find the angle of rotation, what you're going to do is you're going to take 360 degrees and you're going to divide it by your order of rotation, which would be 3. So every time you rotate that triangle, what you're really doing is you're rotating it 120 degrees, okay? And it's a little bit more apparent if we come back, we come back to this one and we bring this one down here, and if we rotate it really quickly, you can kind of see that the shape that you're making is a circle. And so the reason that we use 360 degrees up here is because if you were to rotate this, you would see that you're making a circle. And so there's 360 degrees in the circle. So if you divide that by the number of rotations in the shape, that'll give you your angle of rotation. So take a couple of minutes, see if you can figure out the order of rotation and the angle of rotation for each, the square, the regular pentagon, and the regular hexagon. And then we'll see if we can do the designs too. Okay, so the order of rotation for the square would be 4, so the angle of rotation is 90. And remember, the angle of rotation is measured in degrees, so each one of these would be your angle of rotation, and remember, this is your order of rotation. It tells you how many times you can rotate it. With ones like this, where you don't necessarily have sides, it's a little bit more difficult to see. So basically what we've been saying is, if you can see that there's one design that's being repeated, the number of repetitions for that design is going to tell you what your order is. So for this one, your order would be 3. And so in order to find your angle of rotation, you would take 360 divided by 3, which would be 120 degrees. The Z is a little bit harder to see, so what we've been doing is putting up a Z on the board. And then you can kind of see, if you rotate it, whoops, right tool here. If you rotate it, there we go. Okay, if you rotate it 90 degrees, it doesn't quite look like it did before. But if you take it and you rotate it, there's one rotation. So it's not considered a rotation until you get it to look exactly like it did before. And then if we rotate it back up again, now you can see that you're back to the originals, to the starting point. So the order of rotation for this one would be 2, which means that the angle of rotation would be 360 divided by 2, which is 180 degrees. And then down here, this one's a little bit more tricky, but if you look at the center, you can see that there are 3 little circles in here. And so each one of those represents the number of rotations. So you would have 3 rotations, which means that your angle of rotation would be 360 divided by 3, which is 120 degrees. And then here you can see that this design right here is repeated 4 different times around the outside edge. So your order of rotation would be 4, and 360 divided by 4 is equal to 90 degrees. So your angle of rotation for this one would be 90 degrees. A and B, so what A and B are asking you, A is talking about the pinwheel. So I'm going to go back and grab this pinwheel here really quick. And then we'll bring it back to this page with us really quickly. Okay. We'll just put that up here for now, and then we'll take it off when we need to. So list all the turns of less than 360 degrees that will rotate the pinwheel design to a position in which it looks like the same as what is pictured. What is the angle of rotation for the pinwheel design? Well, what we can do is we can take and figure out what the angle of rotation would be. So the angle of rotation for your pinwheel, remember, in order to figure out what your order of rotation is, there would be 1, 2, 3, 4, 5, 6, 7, 8 rotations. So as you're going around, you're moving like this. Like this. So there's 8 total rotations that you could make. So if you take 360 degrees divided by 8, that tells you that the angle of rotation for this one is 45 degrees. So what it's asking you in this time, list all the turns of less than 360 degrees, is it's just asking you, okay, after one rotation, how many degrees have you rotated this? Well, we know that the angle of rotation is 45 degrees, so each rotation is 45 degrees. So after one rotation, we've moved it 45 degrees. After 2 rotations, we've rotated it 90 degrees. After another rotation, it's 135 degrees. After another rotation, it's 180 degrees. After another, it's 225 degrees, 270 degrees, 305 degrees, and then 360 degrees. And you can tell that you've done it correctly because each time your last rotation should end at 360 degrees. So what you would do is you would list all the turns. That's 45, 90, 135, 180, 225, 270, 305, and 360. So that's basically what you're doing. I'm going to take this off. And that's basically what you're doing for the windmill, the snowflake, and the wagon wheel. So if we look at the windmill, okay, we said that the number of rotations that you could make would be 1, 2, 3, 4. So there are 4 rotations, so 360 divided by 4 is going to give us 90 degrees. So if we start here, after 1 rotation, we've gone 90 degrees. After 2 rotations, we've gone 180 degrees. After 3 rotations, we've gone 270 degrees. And after 4 rotations, we've gone back around, so 360 degrees. With the snowflake, again, if we start right here, we said that there were 6. 1, 2, 3, 4, 5, 6. 6 rotations. So if we start here, we need 360 degrees divided by 6. So each rotation is 60 degrees. So after one rotation, we've gone 60 degrees. After two rotations, we've gone 120 degrees. After three rotations, we've gone 180 degrees. Four rotations is 240 degrees. 5 rotations is 300 degrees. And 6 rotations is 360 degrees. Okay? And then I believe on the wagon wheel, we said that it was 12. So 360 degrees divided by 12 is equal to 30 degrees. So one rotation is 30 degrees, two rotations is 60 degrees, three rotations is 90 degrees, 4 is 120, 5 is 150, 6 is 180, 7 is 210, 8 is 240, 9 is 270, 10 is 300, 11 is 330, and 12 is 360. Okay? We're not going to look at C, but we are going to look at D really quickly. So for each one of the hubcaps below, complete parts 1 and 2 for each hubcap. So basically find all the turns of less than 360 that will rotate the hubcap to a position in which it looks the same as what is pictured. So there's 1 rotation, 2 rotations, 3 rotations, 4 rotations, 5 rotations. So the order of rotation for the first hubcap is 5, so we would take 360 and divide that by 5 to get 72 degrees per rotation. So 1 rotation is 72 degrees, 2 rotations is 144 degrees, 3 rotations is, let's see, 216 degrees. Whoops, is that right? 216 degrees, yep. And then 4 rotations would be 8, 8, and 2. And then after that, we would get 360. Okay? On this one, you can see that there are 3 rotations. So 360 divided by 3 is equal to 120 degrees per rotation. So 1 is 120, 2 is 240, and 3 is 360. Okay? Tell whether the hubcap has reflection symmetry if it does draw all the lines of symmetry. So remember, the reflection symmetry is where we can fold it so that both halves look exactly the same. If we were going to draw the lines of symmetry on this one, they would be through each point of the star. So it would look like this. Okay? And then over here, if we were to draw a line of symmetry, we wouldn't really have one because these figures here are not symmetric, and so even if we draw a line through it here, this is not going to fold exactly on top of this, and this is not going to fold exactly on top of this. So for the second one here, there is no reflection symmetry. All right, so just really quickly, just to think about rectangles and parallelograms. So we've got this rectangle here. If we take this rectangle and if we rotate it, are we going to match up exactly with the original rectangle? So you can see that there's 1 rotation, 2 rotations. So yes, rectangles have rotation symmetry, and then we've got this parallelogram that we can slide over the top here. And if we take this and we rotate it, it matches up with that. So there's 1 rotation and 2 rotations. So rectangles and parallelograms do have rotational symmetry. We've already talked about most of these. The assignment for this is page 16 to 17, 10 through 17, and number 16 is optional. So I've been offering extra credit for 16, but it has to be, the other ones also have to be done. You can't just do 16 and get extra credit. 10 through 17 also have to be finished. On number 10, which of the figures have rotation symmetry? So 10 is kind of a 3-part problem. So you're going to look at questions 2, 3, 4, 5, 6, 7, 8, and 9 from the previous assignment. And what you're going to do is, in addition to reflection symmetry, you're going to look to see whether they have rotation symmetry. So Each one of these should also have an answer as to yes or no. And then for each one that does have rotational symmetry, the second thing you're going to do is you're going to find the angle of rotation. So let's say that number 2 is a triangle. Number 2 would have yes, rotational symmetry, and then it would have, let's see, 120 degrees of rotation. And then which multiples of this angle rotate the figure to a position. So that's when we were listing all the different rotations. So after one rotation, it would be 120, 2 rotations would be 240, and 3 rotations would be 360. So just like we were doing with the previous ones. On number 11, you're looking at which letters have rotation symmetry, and there's not very many. I think there are fewer than 10 that have rotation symmetry, so be really careful for this one, and then give the angle of rotation for each of those as well. 12 through 14, what you're doing is you're using this design that they have. They've basically given you half of the design, and what you have to do is figure out what the other half of the design is going to look like, and then tell the angle of rotation for that design. 15, basically if you just want to trace this and draw the lines of symmetry on it, then find the angle of rotation, and then the number of lines of symmetry for that one, that would be good. 16, like I said, is optional. You can do it if you want, you don't have to, and then 17 is basically just a multiple choice. Hope you're doing well. If you have questions, let me know. Hopefully things are going well, and we'll see you soon.